A collision is just what it sounds like. It's when two objects run into each other, right? Excuse me. And when two objects run into each other, you got, take a simple case where you've got an object moving along and it runs into another object. They bump into each other and then, move off. The time of this collision is very small. And because this time of this collision is very small, we can say that the effects of any external forces are negligible. Like there will be friction, there may be air resistance. If they're colliding in midair, there could be gravity happening. But because the time of collision is so small, none of those forces has an opportunity to change the momentum of the system very much. So in a collision, we say that momentum is conserved. And, I said these things are very small. When I say they're very small, like, they're really, really small. It really is negligible, the momentum that could be lost to friction or other things like that during a collision. So when we have a collision, momentum is conserved, and we're applying conservation of momentum. So our two objects, in theory there could be more objects, but the momentum of our two objects before initially is equal to the momentum of our objects after the collision. That total momentum is conserved. So let's look at an example. Let's say we've got a volleyball with mass 422 grams. It's moving at 2.2 meters per second along the ground when it collides with a basketball with mass 624 grams. Basketball is initially at rest and the collision is head-on. Saying the collision is head-on just means that this is all happening in a straight line. Nothing goes off at an angle, so you don't have to deal with vector components of momentum, which we will do later. Anyway, but for now, this collision is head-on. The volleyball comes to a stop, and the question is, what is the speed of the basketball? So this is a case where we're just applying our conservation of energy. Mass 1, we can call the volleyball. It's 422 grams. Its initial velocity is 2.2 meters per second. The initial velocity of the basketball is 0. So that's all of our initial momentum. The volleyball comes to a stop, so its final momentum is 0. And so we have a basketball with its mass of 624 grams, and it goes off at whatever the velocity of the basketball final is. So you can figure out that the final velocity of the basketball for 422 times 2.2 divided by 624. So the final velocity of the basketball is 1.487 meters per second. Now you may have been wondering why you may have been saying, Mr. Parkhurst, these masses are in grams. Well, they are, and normally we convert to kilograms, but here it doesn't matter because we're taking this mass and then we're dividing by this mass when we move it over, and so the units cancel out. Whether I took 0.422 divided by 0.624 or 422 divided by 624, I get the same answer. I'd also like to consider this. If I asked you to compare the initial and final kinetic energies, or the initial and final kinetic energy of the system. Our initial kinetic energy is just the kinetic energy of the volleyball. It's 1/2. Now I am going to convert the grams because I'm finding an energy times 2.2 squared, which is 0.5 times 422 times 2.2 squared. And we have 0.0212 joules. Our KE final, well, the volleyball has no kinetic energy at the end, so you just have 1/2 times 0.624 times 1.487 squared. So if I punch that in, I get that our final kinetic energy is 0.6906 whatever joules. So note that kinetic energy is not conserved. And in general, kinetic energy in a collision is not going to be conserved. You will lose kinetic energy. So you lose some mechanical energy. And where does that go? Well, a lot of times when there's a collision, there will be a noise. That sound is some of the energy going off into the air. You could also lose some energy deforming the objects. Now, volleyball and basketball will mostly go back to their original shape, but like in a car collision, a lot of times the car will crunch, and you'll lose energy because there's energy required to reshape that surface. And those are the two biggest sources of energy loss in a collision. But I just wanted to point out that this kinetic energy is not conserved in general. It can be, and we'll talk more about that. That's a specific kind of collision if the kinetic energy is conserved. Okay, so let's say we've got another example here. Say we've got a bullet with mass 0.0021 kilograms, 2.1 grams, is moving at 130 meters per second, and it strikes a guy, but he's wearing a bulletproof vest, Kevlar vest. The man has mass 85 kilograms. He's initially at rest, and the bullet gets itself stuck in the Kevlar. And the question is, with what speed does the man fall backward? The reason I'm bringing this up is because in movies, a lot of times you see, somebody gets shot and then they go flying backward from the force of the gun. But let's crunch some numbers here. So our initial momentum is just the momentum of the bullet, 0.0021 times the speed of the bullet, 130. The man's initially at rest, so he has no initial momentum. After the collision, the bullet embeds itself in the Kevlar, so our mass after the collision, the man and the bullet are moving together at some velocity. Now this 0.0021 isn't going to make a big difference if you didn't add it, but in theory it is part of the mass that is now moving. So if I do some quick math here, 0.0021 times 130, and then I divide that by 85 plus 0.0021, that gives me a final velocity of 0.00321, etc. meters per second. So that is how fast this man would be knocked back by the bullet that hits him. When you see people fly backward in the movies, their speeds are probably between 5 or 10 meters per second, which is 1,000 times bigger than that. Anyway, so I just want to point out that in movies, if somebody gets shot and they go flying backward, it's kind of a ridiculous. The physics of that is very shady. At a roller skating rink, we've got Bob with mass of 72 kilograms, and he skates up behind Doug, mass of 81 kilograms, and jumps on his back with speed 4.8 meters per second. And then the question is, what is their speed after Bob jumps on Doug's back and they roll off with Bob on Doug's back? So our initial momentum, we have Bob moving along at 4.8 meters per second. Afterward, the two are together. So this is just like the physics of it is just like the bullet that gets stuck in the Kevlar. Afterward, they're moving together, so the total mass is 72 plus 81, and they have some final velocity. So if we punch this in, we can see that 72 times 4.8 divided by 72 plus 81. Afterward, they have a velocity of 2.2588 whatever meters per second. So if you get extra mass, it's going to wind up slowing you down. I just want to do a more general example here. We got two balls rolling toward each other. Ball A has mass 1.1 kilograms. It's moving at 2.2 meters per second, while ball B has mass 1.8 kilograms and moves at minus 1.6 meters per second. It's going the opposite direction. After the collision, ball A moves at minus 1.3 meters per second. What is ball B's final velocity? This is a more general kind of problem because both objects are moving before the collision. So our total initial momentum, we have the initial momentum of ball 1, which is or ball A, which is 1.1 kilograms times 2.2 meters per second, and ball B has a mass of 1.8 kilograms and it's moving at minus 1.6 meters per second. So our total momentum our initial momentum has two parts. And then that's equal to our final momentum. After the collision, ball A still has mass 1.1, but now it's moving at minus 1.3 meters per second, while ball B still has mass 1.8 kilograms, but it's moving at some unknown speed. So, I mean, the principle is the same. We can punch this into our calculator. Take 1.1 times 2.2 minus 1.8 times 1.6 plus 1.1 times 1.3 divided by 1.8, and we find that ball B at the end moves off with a speed of 0.538 repeating meters per second. So they kind of bounce off each other. But the principle is there that you can put in multiple momenta on both sides of your equation and still figure stuff out if you're given enough information.